a little bit from what we were doing on Wednesday, just a little review of what we ended with in our Wednesday lecture. So in our Wednesday lecture, we were getting into looking at atoms, isotopes, and ions. We were using that AZT, or excuse me, that AZX notation, and we were going after charges and other kinds of things. So to kind of summarize, write the symbol for the ion that has the following number of protons and electrons. 20 protons and 18 electrons. So the charge, remember, charge is always protons minus electrons. So I have 20 minus 18 for a total charge of positive 2. 20 protons, that's its atomic number. Atomic number 20 gives us calcium. So we are talking about calcium with a 2 positive charge. Calcium plus 2. For the second one, 16 protons and 18 electrons, so 16 minus 18 would give me a negative 2 charge. 16 protons corresponds to the element S, sulfur. So this would be S negative 2 sulfide ion. And then finally, 26 protons minus 23 electrons would give me a positive 3 charge. 26 protons corresponds to the element Fe. So this is Fe plus 3. This would be the iron 3 ion. Right? Any questions here? Okay. So that was section 3. Section 4 out of chapter 2 deals with relative atomic masses. Now, relative atomic mass comes from an idea of mass that we associate with a definition. When we look at atomic masses on the periodic table, those atomic masses should give us a little bit of information. First piece of information that they should give us is the average of all of the isotopes that exist for a given element. So we are told by our periodic table that the relative atomic mass for carbon is 12.011 AMUs. Now, as far as carbon is concerned, we know that carbon exists in primarily 3 isotopes. There's carbon 11, or excuse me, carbon 12, carbon 13, and carbon 14. One thing that this mass tells us is that since its mass is pretty close to carbon 12's atomic mass, carbon 12 has an atomic mass of 12, since this mass is so close to carbon 12, then we can rationalize that the majority of the carbon that we see here on planet Earth is actually carbon-12. And so what we get into here is a discussion of something called relative atomic mass. Relative atomic mass is the average mass of all of the isotopes that exist. But it's not a simple average. When I talk about a simple average, I'm talking about most of the kinds of averages we think of, where I add together all of the things that I'm averaging and then I divide by the number of objects. If I want to take the average mass of number of building blocks in a child's play set, I take the mass of one block and then the mass of another and another and another, add them all together and divide by the total number of blocks. That's called a simple average. Another word for that is an arithmetic mean. We're not doing that in this case. Relative atomic masses have to take into consideration two things: the mass of the isotope itself and the relative abundance of that isotope. Not all isotopes are abundant equally. I need to take into consideration both factors: the factor of the mass of the isotope itself and how much of it there is. So from the standpoint of carbon, we know that carbon-12 has a mass of 12. Carbon-13 has a mass of around 13, a little bit more. And carbon-14 has a mass of just over 14. If I did a simple average of those three isotopes, the number on the periodic table for carbon would be about 13. But it's not. It's actually just over 12. Why is that? Because over 99% of the carbon on planet Earth is carbon-12. The other 1% is split between carbon-13 and carbon-14, and the majority of that 1% is actually carbon-13. Less than 1/10 of 1% of all the carbon on planet Earth is actually carbon-14. So it's not a simple average. The mathematical term for this would be a weighted average. And a weighted average is calculated exactly how we are describing here. Taking the individual masses and multiplying by their weights, by their abundances. So let's dive into this a little bit more clearly. A relative abundance is just a proportion, a percent of the substance that is present in that particular isotopic form. So, like I said, the relative abundance of carbon-12 is over 99%. The relative abundance of carbon-14 is less than 0.1%. Those would be their percent abundances. The average atomic mass is calculated by taking that weighted average. And the way to do that is by taking the isotopic mass multiplied by the relative abundance for each isotope, and then adding those sums together, adding those products together. So if there are 3 different isotopes of a given element, I would do that multiplication for all 3 of those isotopes, and then I'd add together the products of each of those multiplications. And that would give me the average atomic mass. Now, this kind of calculation sounds a little bit complicated, but it's actually a lot easier than you think. And I actually have kind of a, I don't want to call it a shortcut because it's not one, but I've got a way to do it that actually simplifies the process a good bit. So let's take a look at an example. Here I have neon. Neon exists actually in 3 different isotopic forms. There's neon 20, neon 21, and neon 22. The 3 isotopic forms of neon have 3 different atomic masses and 3 different abundances. Now, if you read in your book will tell you that you need to turn these percents into decimals before you do your subtraction or before you do your multiplication. I'm going to tell you that that invites far more error than what we're probably comfortable with. What I'm going to tell you to do is this. Multiply these numbers together. Just multiply the atomic mass by the abundance and then add together what you get. We're going to deal with the percentage at the end. But if I do this, 19.9924 multiplied by 90.4838 to 6 significant figures gives me 1808.99. Yes, I know that that number is big. It's not going to resemble anything that looks like an atomic mass at this point. But by keeping the numbers big, it's going to actually make things a lot easier for us when we go to add them together and consider our significant figures. Second one, 20.9940 multiplied by 0.2696. To 4 significant figures, because I only have 4 in the percent abundance, I get 5.660. Last one, 21.9914 multiplied by 9.2465 to 5 significant figures, because there are 5 in this percentage. I get 203.34. My multiplication's done. Now I need to add. Notice how I line these up. I can very clearly see, since I'm adding, what decimal place I need to hold. 2 decimal places here, 3 here, 2 here. My answer is going to be rounded to the 2nd decimal place according to my rules for rounding in significant figures. Remember, when we add and subtract, it's the decimal place that matters, not the number of significant figures. So I add these 3 numbers together, 1808.99 plus 5.660 plus 203.34. I get 2017.99. The 0 there at the end actually rounds out anyway. Now again, 2017.99 doesn't match anything on the periodic table. But that's okay, because that's kind of the point. That's how we know that we aren't finished with the calculation yet. Calculation doesn't make sense. And the reason it doesn't make sense is we haven't done anything with this percent yet. Percent means parts of 100. all of these values have been multiplied by 100. We need to get rid of that 100 value. So we need to take our calculated mass and divide it by that 100. And that would give me 20.1799 AMUs. 20.1799 AMUs. Well, if I look at the periodic table, that's pretty darn close to what the value on the periodic table is. So that's always a good checkup for us. When we're doing these kind of atomic mass calculations, we want to make sure that in the end, we're coming out somewhere near a value that's on the periodic table. If we're completely far away, we're off by a gram, we're off by a couple tenths of a gram. There's a good chance we've made a mistake somewhere, and we need to figure out where that mistake is. So like I said, I don't have a shortcut. This isn't a shortcut, but it does save you a little bit of grief from trying to turn these percentages into decimals first, especially on this one. I can't tell you how many times people have not divided that one correctly and come up with way wrong answers because instead of putting in 0.002696, they put in 0.02696 or didn't solve it at all. Saving that division to the end minimizes some of that random mistake error. All right, any questions on this? All right. We're moving on to the periodic table. And so to that end, I've got something to give you. You may have your own periodic table already. I know there's one in the textbook. I know there's a couple others in other places as well. These are ones that we've had printed up. Put on cardstock. They're nice, they're pretty sturdy. And what we're actually going to do with these is we're going to draw them. Because there are a lot of things that we can draw out of the periodic table just by looking at where an element is on the periodic table. And so we'll be handling that in just a minute here. Some background information. I'm not going to give you a whole lot because, frankly, the history's not all that interesting. Credit for the periodic table of the elements largely is given to a man by the name of Dmitry Mendeleev. And Mendeleev, in a several-year period, took the 63 known elements at the time and started to kind of break them into groups based upon some common properties that those elements had. Now, Mendeleev used one thing in particular as his starting point, and that was atomic mass. The atomic mass of the given substance was what he used to initially order them from top to bottom. And then he was able to kind of arrange them and slide them into groups, leaving gaps wherever there were elements that didn't seem to fit the next spot. So you saw that in the periodic table video that you watched in lab, where there were spots, places where Mendeleev said, okay, the next element should be this, but this element seems to fit here rather than here. And so he left some blank spots in the table. I believe the video referenced germanium, which he called ecosilicon. And based upon common properties and other known quantities in that table, he was able to pretty accurately predict some of the chemical and physical properties of germanium. Here's what we can do. Using our periodic table, we're going to draw out some of the things that have been developed over the past 150 years of chemistry right onto the table itself. So I'm actually going to flip over to the other camera here. Most of what we're going to put on here is stuff that is going to be in the PowerPoint slides here. So you don't need to re-copy everything. If you've got it here, know that there's a reference here for some of the notes that you may not pick up along the way. But let's go ahead and get into our actual tables, because when it comes to doing your homework, when it comes to doing quizzes and things off-site, this is going to be a really valuable resource for you. So first thing that you should notice, this table has actually already been labeled by period number and by group number across the top. Period number reflects the energy levels that are present in that particular atom. So hydrogen and helium, for example, are in period 1. Their electrons are arranged in the first energy level and only the first energy level. The next period, starting with lithium and ending with neon, these have 2 energy levels, and the electrons are distributed amongst the first and the second energy levels. Period here starting with sodium, we have electrons in the first, second, and third energy levels, all 3. So as we go down the table, what we will find is that we have more energy levels available, more electrons to put in those energy levels, and bigger atoms in general as a result, because of those extra electrons, those extra energy levels that are being made. Now let's get into some grouping. Your book outlines 4 groups in particular. This first group I'm going to have to go and get a pen. You know, people have often asked me, why did you want an office on the first floor when all of your labs are on the 3rd floor? And I said, this. If I forget something, I don't have to walk across the street. So this first group here, these are known as the alkali metals. Alkali metals, as you saw in lab this week, are highly reactive with water, highly reactive with air, and generally pretty tough to deal with in terms of You have to store them in a very certain way so that they don't react and don't catch on fire. Right next door to the alkali metals, starting with beryllium and coming down to radium, we have another group known as the alkaline earth metals. Now, as you saw in lab this week, the alkaline earth metals are also reactive with water. They're kind of reactive with air. Actually, they're named alkaline earth metals is primarily derived from the fact that they do react with the air slowly, and that is what allows them to form a lot of the things we find in rocks. And so we find most of these minerals in the earth. But comparing the two reactivities, reactivity here is much, much less for the alkaline earths than it was for the alkali metals. In the middle here, we have two groups of substances. We have what are called the transition metals, so this big block in the middle from scandium on down, these are your transition metals. And then inside of the transition metals, you have these guys, the inner transition metals. And the inner transition metals can be broken up into the lanthanides, the top row, and the actinides, the bottom row. Now, as far as the inner transition metals go, we're not going to spend a whole lot of time with them. Most of these things are either radioactive or so rare that their chemistries are irrelevant to the majority of the people walking planet Earth. Transition metals do have some interesting chemistry, but on the whole, we're not going to touch too much of them other than things that we find commonly in chemical reactions or otherwise. Flipping over, we'll notice a couple of other things. Notice that you have a black line drawn into the periodic table here. This is the line that separates the metals from the nonmetals on the periodic table. And in particular, we want to highlight some of these because these compounds that I'm highlighting in blue here actually have a very special kind of recognition. These blue ones are called the metalloids. Metalloids are kind of special in the sense that they have both metallic and non-metallic properties. So they can be things like they can be shiny, which most nonmetals are not. They can be somewhat pliable, which most nonmetals are not. They can mildly conduct electricity, which most nonmetals are incapable of doing. They're not true metals,
They don't hold any of those metallic properties in great character or great form. But there are some kinds of properties associated with them that we would consider metallic, even though most indications would show that they are largely, mostly non-metallic in nature. On the non-metal side of the coin, so again, on this side of the line, we have our metals. On this side of the line, we have our non-metals. The far right group here, these are known as the noble gases. Noble gases are kind of the opposite of alkali metals, alkaline earth metals, halogens. They are completely unreactive. The last group that we want to call attention to, which I will highlight in this black here, mainly because I'm out of colors. Right here next to the noble gases, we have another group here known as the halogens. Halogens are kind of like the non-metal version of alkali metals. Not because they're reactive with water and air, but because in general they are quite reactive. For non-metals, these are the most reactive non-metals. So alkali metals were the most reactive metals. Halogens are the most reactive non-metals. What we will see is that there are lots of compounds that exist that pair up alkali metals and halogens because of their reactivities in general and because of their reactivities and their kind of parallel nature to each other. One last note that I want to make, and it's regarding charge. We're not going to get too deep into the reasons why yet. But with these groups, because of their position on the periodic table, there are some characteristic charges associated with each family, with each column. Inside of the alkali metals, we tend to see +1 charges. Inside of the alkaline earths, +2s. Inside of the boron group, +3s. Carbon group, we're going to skip for now because it's a little bit complicated. A lot of these compounds don't form ions. The ones that do, lead and tin in particular, actually have more things in common with transition metals than they do with the other substances in their family. Coming back to the other side, the noble gases do not form ions, so they are uncharged. The halogens take on a -1 charge. The oxygen group takes on a -2 charge. And the nitrogen group takes on a -3 charge for the most part. Again, these charges apply only to the non-metals in their groups. When you get to something like bismuth here, bismuth actually has more in common with the transition metals than it does with nitrogen. Bismuth actually takes on more of a +3 charge than anything else. So again, we'll get into more of the reasons why in future lectures. But for right now, this gives us a really good start. And we will be adding more to this as we investigate more and more things out of the periodic table. But for right now, again, you can notice most of the things that we talked about are here in the table. The only thing I did not mention were the things about the diatomic elements, and I'll pin that on to Monday. It'll only take a minute to talk about that. Otherwise, we are completely done with chapter 2. Have a really good weekend.